Hi, today we'll be talking about concept of position, displacement, and distance. In an attempt to describe motion, we are going to be making use of 6 different quantities. The first being position, displacement, distance, speed, velocity, and acceleration. But for the sake of this video, we will only talk about position, displacement, and distance. What is position and how do we use position to describe motion? Position simply refers to where an object is located in space or in a plane. Position is measured in meters and it is denoted with letter X. How do we describe position, or how do position describe motion? We'll be talking about position in one dimension and also two dimensions. From our definition, we say position is simply where an object is located in space or a plane. So because we said in space or a plane, then definitely space refers to 3 dimensions and then a plane refers to 2 dimensions. But how do we describe position in one dimension? In an attempt to talk about position, we refer to a reference point. A reference point. So let's say we have a number line that looks like this. Where this is point 0, this is point 4, this is point 8, and then this is 12. This is minus 4, this is minus 8. And my scale is in meters. So this scale was small enough, it could be in centimeters, it could be in millimeters, and so on and so forth. So let's say I have a point representing an object located at this particular place. What is this point position? So let me call this point X. So it will be X1. All right, so if you look at this scale, you can see my X1 is located directly above -8. So X1 will simply be equal to -8 meters. Let's say I have another point located here. Good. Let's call this X2. If I were to describe X2 position or location, I would simply say X2 is equal to 4 meters. You can see that in order for me to describe my positions for X1 and X2, I always go back to my reference points. My reference points being the origin at point 0. Because on this scale, I know if I move towards the right, towards this point, yeah, I've moved 4 meters away from my reference point or from the origin. If I'm at point 8, I've moved 8 meters away from the origin. So in order to describe an object's location, we always refer to a reference point. Now, how about we want to look at it in 2 dimensions? 2 dimensions. Now, the same logic is true for 2 dimensions and also for 3 dimensions. What do I mean? Let's clear this a bit. Now, let's say we have a plane, an XY plane, that looks like this. This should be my y-axis, then this should be my x-axis. So then this is my origin, point 0. And let's say I have an object located at this point. So let's do our scale again. So this is 2. Let me write that properly. So this is 4. This is 6. This is 8. This is 10. 12. 4. 6. Sorry about that. It should be 8. And it should be 12. Now, this particular object is located in a plane because it has an x coordinate, also has a y coordinate. Let me call this x1. If I were to describe x1's location, then I have to use something called an ordered pair. That is, I will write my x coordinates where my point is on the x-axis, then also where my point is on the y-axis. So if I were to look at this carefully, we can see that this particular object is looking directly above my 8th position. So I can say x1 will simply be 8, comma, then on the y-axis you can say it is looking directly in front of 12. So that becomes 8, comma, 12. And then we describe this object's location successfully. Let's try one more. This time around, let me bring something here. -2, -4, then -6. So let's say we have a point at this place. So let me call this x2. How about you try this yourself? Where is x2 located in? All right, so if you've said x2 is located at, so my x first, so this is -4, then this is 8, so then you are actually right. The way of describing an object's location in a plane or in space is referred to as an ordered pair. Ordered pair. Because we talk about the x first, and then we take the y, and then we join them together in a pair. I hope this makes sense. Moving on to displacement. Moving on to displacement. Displacement. So what is displacement? Displacement is simply when an object changes position or the shortest path between 2 points. Initially, we said position is where an object is located at any point in time in space rather, or in a plane. So what happens when the object decides to change position? How do we describe that type of motion? Hence the name displacement. Displacement also is measured in meters. Measured in meters. And by virtue, let me write this properly, measured in meters. Measured in meters. And also, displacement is a vector quantity. We'll talk about that later on in subsequent videos, what it means for displacement to be a vector quantity. But for now, just have that at the back of your mind. Anytime you hear the word displacement, it is a vector quantity. Symbolically, we represent displacement with a change, which is delta in position. Remember, we said displacement simply refers to an object changing position or the shortest path between 2 points. If this is the symbol, then what is the mathematical implication? Delta x, or change in x, will simply be equal to the final position minus the initial position. Final position minus the initial position. Now, what does this mean in one dimension? Again, let's say we to have a number line like we did previously. Let this be our reference point or our origin. This time, let's increment by factor of 5, 15. Since displacement is measured in meters, we can have meters, we can have centimeters, we can have kilometers, depending on how long or short our number line is. But for now, let's just make do with meters. On our scale, let this be minus 5. Let this be minus 10. And then let this be minus 15. So let's say my object is located at this particular position, and then after a while my object decides to change its position towards this point and stops here in this direction. How do we find how much my object has been displaced by? Come to use our formula, but before we talk about the formula, let's try and analyze what it is, or let's try and compare and contrast. My object initially is at this point, then change position over time to this point here. So it means that I have two locations now. Of course, I have multiple locations, but there are two that I'm concerned about. Where I started from, and then where I'm ending at. If we're concerned about knowing how much my object has moved from its starting position, then I'm talking about displacement. So calculating this, I'll just come here. Since my arrow is pointing towards this particular position here, it means I've moved from this point, which is my initial position, to this point, which is my final position. So my x final will be equal to 5, and my x initial will be equal to minus 10. So my change in x, or delta x, will simply be equal to 5 minus 10, and that gives us 5 plus 10, and that's equal to 15 meters. Now, as far as displacement is concerned, in one dimension, displacement can be positive, can be negative, and can also be 0. The signs displacements have in one dimension tend to account for its direction. What do I mean? If my object is changing position towards the right, that is, it is going towards the right, then my displacement will have a positive value. Note, I didn't say my object has to be on the right to have a positive value. My object can be on the right and then be negative or have a negative displacement. We'll come to look at more examples that will justify that very soon. If my displacement is negative in one dimension, it means my object is moving towards the left. What does it mean for displacement to be 0? Two things. Either the object hasn't moved, From my object moved, let's say from this point, came here and came back to where it's starting from. If I were to calculate the displacement at this instant, my initial position will have been minus 10, and also my final position will be minus 10. So hence resulting in 0. To repeat what I've said, for displacement to be 0, there are two instances. Either the object hasn't moved, or the object moves and comes back to the same starting position. If that is true, then definitely displacement would be equal to 0. Now let's try and analyze what we meant by displacement going towards the right and displacement going towards the left. So let's say we are to have a motion in this, like this, that looks like this. So my object initially is on the 10, and then it is heading towards the right, but stops at minus 5, such a way that looks like this. Okay. Again, from our formula, we know that x final is minus 5, because I'm traveling towards the right. Then x initial is minus 15. Remember, our formula states that x final minus x initial. But from what we've said already, if I have a motion heading towards the right, and if I'm calculating for displacement in one dimension, then it will return a positive value. So let's try and see whether that is true. So minus 5 minus times minus, so that gives us plus 15. So this is plus 10 meters. Plus 10 meters. So that is true for the first instance. So let's check for the second instance. Let's assume my object is traveling towards the left now, and then ends up being on the right. So let's see what we can make of that. Sorry, let's clear this. So let's say we have something like this. So I have this, and then my object is moving in this direction. You can see my object staying at the right, but traveling towards the left. So again, we know displacement delta x is equal to x final minus x initial. So my x final, that is my final position where I'm stopping. If I'm leaving from this point, I'm stopping here. So my x final becomes 5. My x initial becomes 15. So this is 5 minus 15, that's minus 10 meters. So you can see that as far as displacement in one dimension is concerned, then we're talking about an object changing position in a straight line. And since it is changing position in a straight line, then if it is moving towards the right, we say it will have a positive value. The positive value is signifying the direction. That is, we know it is moving towards the right. If it is moving towards the left, we know it is negative. What if it is not in an horizontal line? What if it is on a vertical line, like this? Again, so let's say I have something like this. So again, my reference point 0, this is 4, this is 8, this is minus 4, this is minus 8. So like we did before for the horizontal line, where we pick a direction, that is, if it is going towards the right, we say it is positive. If it is going towards the left, we say it is negative. For the vertical line now, if it is going upward, if my object is being displaced upward, then to have a positive value. If my object is being displaced downward, then it will have a negative value. And for 0, either the object hasn't been displaced, that is, hasn't moved, or moved and came back to its initial position. All right, Now let's move on to displacement in 2 dimensions. But before we talk about displacement in 2 dimensions, I would quickly like us to take a much more complex example. So let's say we were to have a number line again that looks like this. This time around, so this is my origin 0, this is 10, 20, 30, 40, so this is meters, so this is -10, -20. So let's say I'm going to church from my home, and then my home is located at this point. And then on my way to church, I discovered that since I left my wallet at home, and then I have to, pay tithes and offering. So what do I want to do? I want to go back home, pick my wallet, and then head back towards church. And then let's say church is around this particular position, somewhere here. If I were to calculate for displacement, I'm only concerned about 2 positions. My initial point here, do my arrow, and my final point at this particular junction. That's to tell us that displacement doesn't really care if there is a turning point or not. In as much as we can get the initial position or the starting point and then the final position or the ending point, then we can always calculate for displacement. Displacement won't tell us what has happened in between, whether there's a turning point, whether you forgot something, whether you left something out, whether you went to branch to visit your friend. Displacement wouldn't tell us that. It's only concerned with the starting point, which is x1 or xi, and then the final point, which is xf. So if I to calculate displacement in this case, my displacement will simply be xf minus xi, so that's 20 minus 20, and that gives me 40 meters. But you agree with me that 40 meters is not the total path taken by this object in this motion that we've tried to describe. Now, when we talk about distance, we continue from this point. But for now, let's take displacement in 2 dimensions. For displacement in 2 dimensions, definitely we're trying to look at how an object has been displaced in a plane or in space. Like we said for position, the same logic applies for both. So let's say we have a plane, an XY plane, like this. This is my origin. Let's say this is 5, this is 10, this is 15, this is 20, this is 25, this is 4, this is 8, this is 12, this is 16, this is -5, this is -10, this is -15. All right. So if I were to have an object at this point initially, and then I have an object at this point finally, because like our definition, shortest path between 2 points, displacement. Now, let's say our object is traveling in this direction. Let me call this x2. Let me call this x1. Now remember, we said x represent position. I don't mean the x plane or the y plane. Okay, so this is my y axis. Let me write that properly. And then this is my x axis. Now, x2, from my knowledge of position, if I were to describe this, I would say x2 will simply be x subscript 2, comma, y subscript 2. Then x1 will simply be x subscript 1, comma, y subscript 1. Remember, we're trying to look for how we can find the displacement between these two points. Now, from geometry, if this is my origin, from the origin here, if I were to trace this line down in such a way that looks like this, so it means from this origin to this point is simply x2. From this line here, from this origin here to this point is given as x2, like this, like this. Okay? And then from this origin to this point, from this origin to this point is given as x1. This place to this place is simply x1. So it means if I'm looking for the distance or the length between this remaining place, I simply need to say x2 minus x1. All right. Now moving to the y-axis. Again, at this point, let's say from the origin to this point, where my x1 is located, I can say it is my y1. Then again, from this point, my position 2, I say this is simply given as y2. That means looking for the length of this place to this place will simply be equal to y2 minus y1, isn't it? Now let's flash back to mathematics, Pythagoras theorem. If I were to complete this triangle in such a way that it looks like this, so it means the length or the base of my triangle from this point to this point will simply be x2 minus x1, and then the height of my triangle from this place to this place will simply be y2 minus y1. So the distance or the length between these 2 points, remember when we said displacement is simply the shortest path between 2 points. So it means that the length between these 2 points, x1 and x2, let's say it is r will then be given by the square root of x2 minus x1 all squared plus y2 minus y1 all squared. This is gotten from Pythagoras theorem that states that a squared must be simply equals to b squared plus c squared. Our b now is simply x2 minus x1, and then our c, y2 minus y1. So this is the formula we want to be conversant with in solving displacement in 2 dimensions, in as much as there is no turning back. Of course, for typical questions like this, or the questions we are going to come across mostly will always involve the ones with no turning back. And for the ones with turning back, then we use our xt graph to solve. Now let's quickly solve this question before we talk about distance. So what is my x2? So here I can say r will simply be equal to the square root. So my x2 is simply 20. Remember, this is x2 here. So 20. x2 is 20 minus x1 is 10. 20 minus 10. Okay. Then everything all squared plus, then what is my y1? Sorry, y2 rather. So y2 will simply be equal to 12. That's 12 minus, what is my y1? So y1 is 4. 4, then squared. So this is equal to 20 minus 10, that's 10. 10 squared is 100. So 100, 12 minus 4, that's 8. 8 squared, 64. So we have 100 plus 64. And this gives us the square root of 164 units. All right, so that's how we calculate for displacement in 2 dimensions. Moving on to distance. All right, so now we talk about distance. What is distance? So we simply refer to distance as the actual path taken by an object in space or a plane. We refer to distance as the actual path by an object, the actual path taken by an object in space or plane. Distance is represented with small letter d and it is measured in meters. Unlike displacement, that is a vector quantity, distance is a scalar quantity. Of course, I did say we're going to make a separate video where we look at the concept of vectors and scalar. But all we need to know for now is that vector involves the magnitude and also the direction of that particular quantity. While for scalar quantity, we're only concerned with the magnitude. Things like height are scalar quantities. For instance, if we were to ask about your height, you tell me your height is, you just give me a specific number, maybe 5 feet, maybe 90 centimeters, maybe 110 centimeters, maybe 6 inches. Those are all scalar quantities. Imagine I were to ask for your height and then you are telling me something like minus 4 feet. So the first thing that comes to my mind is, are you going backwards or upside down? Whatever. So it doesn't make sense. So quantities that only have positive values are usually referred to as scalar quantities. We'll talk more about that when we talk about scalar and vector. Now back to distance. So like what we did for displacement, where we took displacement in one dimension and also displacement in 2 dimensions, are going to be doing the same for distance. So distance in 1 dimension. Let's say we are to have a number line again. This time around, we have a line that looks like this. Okay. And then let's assume this is my reference point 0. This is 0.5. This is 0.10. This is 0.15. 20 minus 5 minus 10 minus 15 minus 20. Let's extend this a bit. 25. I have coming from negative infinity to positive infinity. And my scale, as always, is in meters. So my scale can be in meters, can be in centimeters, any unit of meters, or any unit we use to measure length will suffice. All right. So now we're going to be calculating for 2 things. We calculate for displacement first, and then we calculate for distance. So this is just an effort to say that distance and displacement are necessarily not the same thing, even from their definition. In as much as some textbooks try to interchange it, they are only the same in a specific instance when there is no turning point. But if there are turning points, then definitely distance and displacement won't be the same thing. So like always, let's assume that we have our objects located at point 15, and then we have the objects moving towards -5, and discover that, oh, it seems I left something where I'm coming from, then goes back, picks up the thing he left, then heads out once again up onto this point. On getting here, perhaps he saw something he likes and then decides to turn back to check it out. So checking it out, then after checking it out, move to your final position at this point here. All right. So now we have different points that we want to note. But when we calculate for displacement, this point here, this point, let me call it x1, and this point, let me call it xf. I don't want to call it x2 because I have different points. I have a point here, I have a point here, I have a point here, I have a point here. So basically where you're starting and where you're ending are the points that you want to be concerned with. But as far as displacement is concerned, I only need my starting position, which is here, or my initial position, and then my final position, which is here. So calculating for displacement here, delta x, as always, this will be x final minus x initial. So my final position is 20. My initial position is minus 15. Sorry, okay, there should be a minus here. So minus, then minus 15. So this gives us 20. Right, that quickly. 20 plus 15, and 20 plus 15 will definitely result in 35 meters. So as far as this motion is concerned, at this particular moment, if you are to find displacement will tell you your object has been shifted or displaced 35 meters from its starting position. But that's not what we are concerned with. We want to know the total length or the actual path taken by my object in this motion, hence the name distance. Now for distance, we are going to be calculating distance the same way we are calculating displacement at every junction. What do I mean? From this part, this point here to this point, let's assume it is D1. That's one part, the length. So if I'm traveling in this direction, then this other one, so I'm starting here at this point and then I'm ending here. So let me call this D2. Sorry, I didn't write that properly. Let me call it D2. Then from this point to this point here, let me call it D3. From this point to this point here, let's call it D4. And then lastly, from this point to this point here, let's call it D5. Definitely, if I know what D1 is, if I know the length of D1, and I know the length of D2, I know the length of D3, I know the length of D4, I know the length of D5, then definitely I can know the actual path, the total length, or the actual path taken by my object from this point to this point. So we're going to be using our knowledge on displacement, but let's quickly write our displacement answer somewhere here. So we're going to compare our final answers. So delta x, we say it is equal to 35 meters. So clearing this place, so we can have enough space to work for distance. So we're saying the total distance, d total must be equal to d1 plus d2 plus d3 plus d4 plus D5. All right. Now, earlier I said we're going to be solving for distance the same way we solve for displacement. But we're going to be using a condition. If I were to have a negative answer, I will only take the positive value or the absolute value of that particular answer. Remember, we said displacement could be positive, displacement could be negative, but distance can only be positive. So if I were to solve for distance, the same way I'm solving for displacement, and I'm having a negative answer, I'll only pick the positive value and leave the negative sign. Because we already agree that the signs just tells us the direction in which we are traveling. Distance doesn't care about direction, so we only take the magnitude or the value or the positive value or the absolute value. All right, so for D1, my starting point is at minus 15. Yeah, my ending point is at minus 5. So originally, I know x final minus x initial. My final point for D1 is minus 5. My initial point for D1 is minus 15. Minus 5 minus minus 15, that's minus 5 plus 15. So that will give me 10 meters. So that's for D1. For D2, D2 will simply be exactly the same thing. If I were to take a ruler and measure this, I'll get the same thing as when I measure from here to this point. But let's try and solve so you don't get confused. But now, what's different between D1 and D2? You can see for D1, I'm traveling towards the right. For D2, I'm traveling towards the left. So that means my D2, my final position is minus 15. My initial position is minus 5. So here I would have minus 15 minus 5, and this gives me sorry about that, it should be 2 minus 15 minus 5. So that's minus 15 plus 5, so that will give me minus 10 meters. But distance can only be positive, can never be negative, so I only take the positive value here. So my D2 is equal to 10 meters. If I were to calculate for displacement, I'll leave my final answer as a negative in its sign. But for distance, you always take the positive value. All right, for D3, so let's try and work here. D3. Now, again, for D3, I'm stopping at this point, so which is on 10, and then I'm starting at minus 15. So my final point will simply be 10 minus minus 15, and this is 10 plus 15. 10 plus 15 gives us 25 meters. That's for D3. For D4, again, come to my graph. So for D3, I'm traveling in this direction. For D4, I'm traveling in this direction. For D5, I'm traveling in this direction. So for D4, I'm starting here at 10 and I'm ending at minus 5. So D4 becomes minus 5 minus 10. So that gives me minus 15 meters. While D5 will simply be equal to, again, I'm stopping, but my final position is on 20 and my initial position is on minus 5. So that will simply be 20 minus 5, and that's 15 meters. So my total distance, D total will simply be equal to D1 plus D2 plus D3 plus D4 plus D5. So this is plus, and it looks like a T, it's plus. Okay. Now, D2, so my D1 is 10. So 10 plus D2, 10 plus D3 is 25 plus D4 is 15 plus D5 is also 15. So this will be equal to 10 plus 10, that's 20. 20 plus 25, that's 45. 15 plus 15, that's 30. 30 plus 45, that's 75. So the total is 75 meters. So this means that my object has walked a total length of 75 meters during the course of this motion. So you can see that displacement and distance do not mean the same thing, only in a special case. Of course, but to calculate displacement between this point and this point, I have the same thing as distance. So we can say, come to a conclusion and say distance will be equal to displacement when there is no turning point, when there is no, sorry, let me write my S very well, when there is no turning point. Turning point. But in as much as there's turning point, then distance can never be equal to displacement. Now, if you look at this, when we said distance is equal to displacement, so I didn't just write displacement. I said the absolute value without the sign. Remember, plus 10 is different from negative 10. All right, so quickly, let's move on to distance in 2 dimension before we call it a day on this video. Distance in 2 dimension. Okay. All right, now for distance in 2 dimension, so it follows the same logic as displacement, follows the same logic as displacement. But this time around, we're just going to be looking at an object traveling along a path without a turning point. And when we talk about our xt graph and vt graph, we look at where our turning point will be. Remember, if there's no turning point, we said distance and displacement would be equal in magnitude only. But if there are turning points, then distance and displacement would never be equal. So again, let's take a point here. Let me take a point here. Let me call it x1. Let's take a point here. So let's call this x2. Now x1 will have an ordered pair of x1, y1. x2 again will have an ordered pair of x2, y2. Okay, if I were to find the distance between these 2 points, again, since there's no turning point here, I'll just use the same thing I did for my displacement using Pythagoras theorem to complete my triangle, and then using that to find the missing side. So we'll just come here and say r will be equal to the square root of x2, let me write that properly, and let me draw my square root properly also. So r, so if the distance between this place is called r, then definitely would have x2 minus x1 squared plus y2 minus y1 squared. So that's how we find our distance, in as much as there's no turning point in 2 dimension. If there are turning points in 2 dimension, then we can come to use this formula. Then we have to be using, either we use something called the area of our shape when we talk about a vector graph, or we just calculate our distance in section, like what we did in 1 dimension. But not to worry, we'll do all these examples when talk about interpretation of our xt and vt graph. All right, so that's all we have for today. Do well to share, like, and subscribe to the channel, and also drop your comments or your suggestion in the description box, and then I'm going to try as much as possible to go through all of them. So thank you very much.